All right, probability for statistics. So we're going to start with a, an event and simple event and sample space. So event is a possible outcome, a set of possible outcomes, like things that can happen. A simple event would be an event that cannot be uh, broken into simpler events. And I'll explain what these words mean by giving you some examples. And sample space is the set of all simple events. And to explain these concepts, let me talk about throwing dice. So often when you play a board game, you throw 2 dice, right? So if you throw, so example, throw 2 dice, then you have several possibilities. You might get 2, right? And you could be get a 3. That's a possibility. So that's an event. That's an event. Okay, right? These are all the possibilities. Right? However, this is you can only get 2 in one way. What is it? By rolling a 1 and then a 1, right? But to get a 3, you could have 1 in the first roll and 2 in the second, or you can have 2 in the first and 1 in the next, right? So if you compare these two, you see that this one is actually not only an event, this is a simple event because it's just made of one exact thing, right? There's only one way to get it, right? Whereas this one is not a simple event. It's actually made up of 2 simple events. Does that make sense? Okay. All right. Uh, so now think about the following question. If you play a Monopoly, what number comes up the most amount of times? If you throw 2 dice, what number comes up the most number of times? Yes? Huh? No, no, no. As a sum of the two. Yeah. Yes? You think 8? Yeah? You got a lot of 12s. Okay. What did you usually get? 11? Oh, okay. All right. Yeah. 5. All right. I get so many different responses, but when I was playing Monopoly as a kid, I noticed that 7 comes out the most often, and I was wondering why it is. So I actually made a table to see why that is true. So I made this probability space, which is like number 1 and number 2. So you could have the number 1 dice to come up as 1, 2, 3, 4, 5, 6. And you can also have 1, 2, 3, 4, 5, 6. Yeah, I was 6th grade when I was thinking about this question. Yeah. Oh, by the way, judging from the answers that you gave me, don't ever gamble. All right, you're always going to lose. All right. Yeah. Okay. All right. So you have to understand probability in order to win by gambling. All right. Okay. So this would be like getting a 1 and 1. This one, two is the first row and 1 is the second row. This will be 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, and then you get 1, 2. Yeah, but you see what I'm doing? Yeah, I'm just writing down all the possible outcomes when you roll a dice, roll 2 dice, right? So 3, 2, 4, 4, 2, 5, 2, 6, 2. Let's see, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3. This is taking a long time writing, but let me be quick, okay? So 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 5, no, 6, 4, and then 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, 5, and then 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6. All right. So you get that. And the things in blue, what do we call it? It's a collection of all possible events, all possible simple events. What do you call that? Yes? Sample space. That's called the sample space. So things written in blue is what we call the sample space. All right. Now, when you have sample space, then we want to verify or we want to find an explanation why getting the 7 is the most common occurrence when you play either the Monopoly or do you guys play Catan? Some of you do? Yeah, yeah. It's a really great game, right? Okay, so in Catan, if you get a 7, then it's a bad number. But it actually, you get unlucky quite a lot of times, and you'll see why, right? Okay. So now let's talk about the random variable. And a random variable is it's a numeric value assigned to each event, each simple event, sorry. Simple event. Now let's think about what numeric value we are interested in on here. We're talking about the sum of the 2 die, right? Two dice, right? So when I roll 1, 1, I'm thinking of 2, right? So that will be our x. So in our example here, x will be the sum of dice. All right. And then now we are ready to define probability. Okay, so probability probability but you know, rather than having somebody tell you what it is, you already know a lot of these things. You have the intuition. So let me ask, first, how large is this sample space? How many simple events do you see? 36, 6 times 6, right? So what's the chance that you're going to get 1, 1? 1 out of 36, right? You're going to get the number 2, only 1 out of 36. You get it? Okay. What's the chance that you get 3 when you roll the dice? This can give you 3, this can give you 3, right? So you get these 2 possible simple events out of 36. You do 2 divided by 36, which is 1 out of 18. Okay, or 2 out of 36, which is 1 out of 18. That's the probability. You have to make sense out of this, okay? Do not try to learn math without really understanding it, okay? And I know that one of the problems is that some of you feel that, oh, I never understand math, so I'll just memorize whatever that's thrown at me. Don't do that, okay? That's the way to fail this class, right? I want you to understand first, and then only after you make sense of it, that then you can decide on which one to memorize and which one you don't. So I'm going to write a formula, but hopefully you don't feel like you have to memorize this formula because it's so natural, right? Yes, you have a question.
Can that be like a value assigned to each sample space?
So the question was, should this be value assigned to each sample space? No, it's a value assigned to each simple event. So simple event are these things, each one of them.
But they only happen once, though? Can't be.
It's once, but these are the outcomes, right? So these are for each outcome, a value can be assigned, right? So if this is 1, 1, the way for this example, the value we're assigning is 2. This example, the value we're assigning is 3, so on and so on. Okay, all right. Okay, so I'm going to write down the formula for the probability. And let's say A is an event. So it could be a simple event, or it could be made of many different events. Okay, and it's the ratio of all. So number of simple events. So number of simple events that belong to A divided by the number of simple events. Okay. And by number of simple events, it's the size of the sample space. Okay. So you're dividing by the number of events that belong to A, and you divide that by simple events. Okay. Okay. Now using that definition, let's try to calculate the following. What's the question again? A is an event. An event is made up of several simple events, or it could be just a simple event itself. Okay. All right. So let's think about the question. What is the probability that you get 7? Okay. Now on this table, can you identify the simple events that where 7 is assigned to? Which one gives you 7? Give me one. 3, 4. 3, 4 would give you a 7, right? Because if you add the 3 and 4, you get 7, right?
6-1.
Huh? 6, 1 as well. 5, 2. 4, 3. 2, 5, 1, 6. Do you find anything else? Do you find anything else? No, that's all, right? Okay, how many simple events do we count? 6. What's the size of the sample space? 36. So we get what? 1 out of 6. So that's the probability. Now, think about what other uh, what other other numbers will have as probability. So probability of someone said, "Oh, I get 5 a lot." Well, what's the probability of this one? It's this one, 2, 3, 3, 2, 4, 1. So it's these 4, right? So you have 4 simple events out of 36, which is 1/9. Okay, which one's bigger? 1/6 is bigger than 1/9, right? So if you do this for all of them, you'll see that you can actually make a table out of this. So let's make a probability table for the x and its probability. Okay. All right. You can't get 1 as the sum. The smallest you can get is 2, 3, 4, 5, 6, 7, and I don't have any room for it, so I'll make a second table here as a continuation. 8, 9, 10, 11, and 12. And it works like this. This would be like 1 out of 36. This would be 2 out of 36, 3 out of 36, 4 out of 36, 5 out of 36, 6 out of 36. And then starting 8, it goes down again because to get 8, you have 2, 6, 3, 5, 4, 4, 5, 3, 6, 2, right? So this would be 5 out of 36. What's this one? 4 out of 36. And these are the probabilities that each numbers can show up when you throw a dice. Okay, when you throw a set of dice. Okay, and it proves why 7 appears the most. All right, 7 appears the most. Okay, you should know these things. Yes, you have a question.
So, for an exam, would we be required to write out a sample space of that size, or is it just going to be like?
We'll see. We'll see. Okay. This is. I'm doing this example because it gives you a very good conceptual understanding of everything. But once we extract the basic properties and you can kind of gain insights into this, then I'll give you some other random stuff and you'll be able to understand the others as well. Okay. Yeah. Yeah. Don't be too focused on this one example. Just try to gain the general principles behind probability, right? Okay. All right. Now the next, yes.
So, just to clarify, that A,
Uh-huh.
that's just a random variable.
No, A is a set of simple events, but sometimes a set of simple events can be expressed by a random variable. Actually, that's a question. That's a nice question. So the question is, what is this A? And A is set of simple events, but sometimes setting x equals to something like this, this is a composite event, right? Because there are 6 different simple events that make up x equals to 7, right? So the moment when you say x is equal to 7, you're really saying, give me the probability of getting this one or 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 this. That's what's being asked. Okay. So this is same thing as saying, what's the probability of this set where you have 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. Right? And this set is what we call A. Okay? But instead of writing it like this, often what we're interested in is what's the probability of some random variable taking certain value. Okay? Yeah. So that's so we never write it like this, but if you insist, we can write it like this. Okay. All right. Okay. So now this can be seen like a frequency table, except that it's not the actual frequency that's written here, but it's like a relative frequency that appears. Okay, so there are actually two different ways of looking at probability. Some people might say, well, the definition of probability is that if you repeated this experiment 10,000 times or a million times, right? And if you look at the frequency distribution of which x value you get, then you would see that their relative frequency will come up exactly like this. Not exactly, but it will get closer and closer. That's called the law of large numbers. But some people would say, well, see, because once you have this sample space, when you see the sample space, you kind of can judge for yourselves that the probability of getting a 6-6 or 1-1 or 2-1, each of these should have the same amount of probability, right? So you can assign probability before you do the experiment, and that'll be like a theoretical probability. And the law of large numbers, which is proved, it's a mathematical theorem, and the statement is that if you repeat certain things many, many times, then the more you repeat, the frequency probability, the probability that you get by looking at the relative frequency, gets closer and closer to the theoretical frequency that you have. Okay. But sometimes, yes, you have a question.
All the numbers you circled, those are like sample space.
The numbers I circled is what I circled this one when we were looking for 7.
Are they like? Can you call them sample space?
No, sample space is this entire blue thing. Okay. Yeah, sample space is the entire thing. Okay. The ones I circled was the event which gives you x equals to 7. All right. Okay. So where was it? Oh, all right. So sometimes you want to win against the house. The house always wins, but let's say you wanted to cheat, right? Then what do? You make your own die where you have one side heavier than the other. So you have a cube where one side will be heavier than the other. So if you roll it, you might see that the number of ones might come much more often than the other ones. Can you imagine something like that? Right? So if that's the case, then it's no longer true that all of these simple events have the same probability. Okay. In that case, we can't use this formula anymore. Rather, what we have to do is the probability would be a little more confusing. I refuse to write it because it's not really important for us, but it would be more like sum of all the probabilities of the simple events that belong to A, and divided by the sum of all the probabilities of simple events. But the probability of everything is always 1, so this is not needed. So that's a secondary definition if it turns out that your sample space doesn't have uniform probability, right? So that there's actually, I wrote this formula, but that's only when you can have a hypothesis that all of these outcomes are of equal probability, right? Okay, so with that understanding, now let's talk about expectation values. So expectation value, or E of x, is like taking this table and treating this as a frequency table and finding the mean value, right? How do you take the mean value when you have a table, frequency table? So 2 appears this number of times, 3 appears this number of times. So what do? 2, and then you multiply them. And that was the answer I wanted. So you multiply 2 times 1 over 36, 3 times 2 over 36, 4 times 3 over 36. And do all that. You add them up, okay? And you divide it by what? The total frequency. If you add this, you get some number and you divide it by that number. That's how we do it for frequency tables, right? Is that good? Right? Yeah. You simply multiply. I know you're doing a quiz on this soon, so if you don't know, that's not good, right? So in frequency table, you just multiply across, add them up, and divide by the total, right? Okay. However, there's one more thing that's different when you're working with a probability table, because if you add up all the possible probabilities, what do you get? 1. You get 1, because so what's the probability of any of these happening? Well, that's like 36 out of 36, right? Which is 1. Is that right? So if you added all these things, you'll end up with 1. That means you don't have to divide it by anything at the end, because dividing by 1 doesn't do anything. Understood? It's good? Yes?
I know you were saying we were supposed to multiply in the frequency table.
Yeah.
I don't remember multiplying at all in the frequency table.
All right, so the question was, why do we multiply in the frequency table? Let me just, don't write this, if you're taking notes, you're just going to, it will just look confusing, but if you have 2 appearing 3 times, 5 appearing 4 times, 7 appearing 2 times, what's the average? How do you do that? Well, the long way would be 2 plus 2 plus 2, 5 plus 5 plus 5 plus 5, plus 7 plus 7, and then you divide by how many? 7, 9. You divide by 9. That's how you take the average, right?
Oh, yeah.
Okay? Now, but writing this 3 times, that's not good, right? You have to be smarter. What do?
2 times 3.
You just do 2 times 3. What do you do here?
5 times 4.
5 times 4, and then 7 times 2. What just happened? We multiplied these and added them and divided by the total number of things, right? Okay? So that's what I meant, right? So if you weren't following me when I was talking about the frequency table, that's what I meant. And now coming back, here's what the expectation value is. It's like sum of, you add up all the xi's times the probability attached to it. So I'm calling this one as x1, p1, x2, p2, x3, p3. You multiply them, you add them. And finally, you have to divide by something, but dividing by 1 doesn't do anything, so that's it. That's all there is. That's the expectation value. Does it make sense? Is that good? Yes. So here we did this times this, this times this, this times this, and added them up, divided by 9, right? Okay. Why 9? Why 9? Can somebody explain? Why 9? You have 3 objects, 4 objects, 2 objects. If you add them, what do you get? 9. So we divide by 9. Okay? All right. So look here what we are doing. We have several things. You multiply, add them up. If we add these up, we get 1. So I have the, so really what we should be doing is, we should be doing this and dividing by sum of PIs, but the sum of PIs is equal to 1, so that's not needed. Does that make sense? If you understand, please nod, because I have to go on, right? If you don't nod, I can't, I'll end up explaining the same thing over and over again, okay? So try to work with me here, all right? Okay, so for this one, if you actually tried, here's what's going to happen. So for this example, you're going to get the expectation of the number of rows will be, it'll be like 2 times 1 over 36 plus 3 times 1 over 30, 3 times 2 over 36, and then just do all that until you reach plus 12 times 1 over 30, 12 times 1 over 36. Just multiply, and you add them up, and you're going to get 252 over 36, which gives you 7. So even the mean value is 7 as well. Okay, not only 7 is the mode here, the mean is also 7. All right. Okay, now let me try to give you another example by introducing a second kind of random variable. So this time, let's say y is a random variable, and let's say your friend is, you're making a bet with your friend. So here's what you want to do. You give him the dice, and the 2 dice are thrown, and if he gets a 7, you pay him $100. Okay. If he gets 2 or 12, you give him $200. Okay. And if anything else, there's nothing. Right. So it could be like an event or a bet or anything like that, right? And we're going to think of this as our y value. Okay. All right. So can you make a probability table for it? So the question is, what is the expectation value of y? That's the question. So let's try to answer this. So you can earn $0 or $100 or $200. Okay, first $100. What's the probability of getting $100? Huh? Probability is always between 0 and 1. Okay, so it's 1 in what? 1 in 6, right? It's this one. Getting a 7 is 6 out of 36. So it's 1 in 6. Okay. What's the probability of getting $200? What is it? 1/18th, right? Why? You have 1 in 36 of getting 2, 1 in 36 of getting 12, right? You add them up, you have 2 out of 18, or the 1 out of 18 probability of getting that, right? Okay. Now, for this one, we now have to add everything, but rather than doing that, the probability of something not happening is just 1 minus the other one. So what's the sum of these two? So let's try 1 over 6 plus 1 over 18. Multiply 3 top and bottom. So it's 3 over 18 plus 1 over 18, which gives you 4 out of 18, which is like 2 out of 9 if you reduce. So that's the sum of these two probabilities. So what's the probability here? 7 out of 9. Okay. Now, once we have the table, we are now ready to calculate E of y. So E of y is equal to what times what? 0 times 7 over 9 plus 100 times 1 over 6 plus 200 times 1 over 18, right? So that's 100, that's 50 over 3 plus 100 over 9. So if you multiply 3 top and bottom, you get 250 over 9. Okay? And what is that? That's like 20, 1870, 20, about $27, $26 and something. Okay, so if they charge you $30 to play this game, are you going to lose money or win money? Lose. Okay. If they charge you $20 to play this game, do you play or not? You do play because you're going to win if you do this repeatedly. Okay, so that's the expectation value. It's all about gambling. You know, the entire discipline of probability was developed after people thinking about gambling problems. Okay, they were trying to see what's the fair way to divide gambling money if the game was stopped in the midway. And that was like the beginning of probability. But the real use of probability is actually statistics. And you'll see later in this class that statistics can tell you a lot about the entire population when you only have a sample. Okay.